So here we have a coplanar force system, and what we intend to do with this system is to calculate the magnitude and the direction of the resultant force. And in addition, we want to find exactly where that line of action will be and the perpendicular distance of the line of action from the pivot point. So the first thing that you want to be able to do is to understand how to calculate force components. And force components is simply whenever we have a force at an angle, let's say a force like this one, I'm drawing in purple, and I'll just do a dotted line to represent the origin for the reference. So here we have the force and the angle is right there at the center. And all force component is whenever we have inclined force, we have to break that up into horizontal force components, which looks like this. So HC for horizontal component, and you will just simply do force multiplied by cos and then the angle. So all of this will be much clearer when we're doing the actual calculation. So for vertical force components, it's similar, but we'll change that cos to sine. So force, sine, and then the angle. So that's step one done. So you have to be able to do this first in order to really understand how we're going to put together the calculations. Now, the second thing that we need to understand is how to determine whether or not our force components are positive or negative. And to do this, I'm just going to sketch a coordinate grid. So it's a rough sketch, and the vertical axis will represent our vertical force components. Horizontal axis represents our horizontal force components. And above the horizontal line, these values will be positive, so that's a plus. Below, negative. And to the right on the horizontal line, that's plus. And to the left, that's going to be minus, just like your coordinate grid. And as a standard rule of thumb, when I put the plus or minus, what that should mean for you is the top value is our horizontal component, bottom value our vertical components, just like we do with vectors. So let's say we have a force going like that, so it's going up and it's going to the right. So in this quadrant, both our components will be positive. So if the force is going up and to the right, it means our horizontal component is positive, and also our vertical component, because it's going up, it's going to the right. Now, let's say the force is going down and to the right. So in this quadrant, you can see that we're going to the right. So therefore, our horizontal force component, it must be positive still. But we're going down. So it means then that our vertical force component will be negative. Let's do another one. So this time around, we're going down and we're going to the left. And what that means is our horizontal force component, negative, and also our vertical force component. Why? Because we're going to the left, so therefore horizontal values will be negative, and we're going down, so therefore our vertical values will be negative. And then let's do the final one. We're going up and we're going to the left, and I'm sure you get the idea by now. So we're going to the left, so negative for horizontal components, but we're also going up, so positive for vertical components. And this is what we'll use to determine whether or not our force components are positive or negative. And with this knowledge, we can go into doing the calculations now. So I'm going to start the calculations by just simply labeling my forces, just so that I'm quite clear as to what I'm doing. So I'm going to use F1 as the 50 newtons, and it's at an angle. On the diagram there, you can see the angle as 65 degrees, which I've just highlighted in yellow. So 50 newtons at 65 degrees, just to be clear. And then we are going to label F2 as 40 newtons. So that's going to be 40 newtons. And that 40 newtons, it's just simply going to the right. So it's just at 180 degrees, but we don't use that as an angle for now. Let's go to F3, and for F3, I'm going to label F3 as my 30 newtons, and similarly, this one's just going left. Finally, F4, which I'm going to label as the final one, which is 90 newtons. And that 90 newtons, it's at an angle of 50 degrees, which is denoted right here, highlighted in blue. So now for the main event, the calculations. So for the calculations, I like to organize my calculations on a table, and that is to give me maximum clarity and efficiency in just seeing exactly where I'm at with my calculation. So it's just going to be a rough sketch of a table. And on the left side, this is where I'm going to put my forces. In the middle, that's our 8C for horizontal force components and VC for vertical force components. So to begin with, I am going to start with our first force of 50 newtons. Now, this 50 newtons, we've already established that it's going down and it's also going to the right. So this is where our sign conventions come in. So because this force is going to the right, it means then that my horizontal component, first of all, will be positive. So I'm just putting a plus there. Don't have to, but just to emphasize. And then it's going to be force, which is 50, cos, and then angle, 65 degrees, just like we have done before in the demonstration. Then you have to put that in your calculator to get your answer, which turns out to be 21.13 newtons. So that's the first force there. Now, when we go across to the vertical force component, this force is going down, so it's going to be negative, and it's going to be similar. So 50, sin, and 65, and once again into your calculator, and that's going to give us negative 45.32 newtons. So for the 40 newtons, you will notice that this force, it's just literally going to the right. So there's no angle to it. It's just an horizontal line that's going to the right, an horizontal force. So what that means is we're not going to use any cos or any sin with this one because it has no inclined angle to it. So this is just simply going to be 40 newtons, no calculations required for this one. And it's 40 newtons for the horizontal component, and we need to also see that it's positive because it's going to the right. So for the vertical force component, it's just going to be 0 because it's not at an angle, it's just purely horizontal. So moving on then to force 3. Now that that one's out the way, moving on to force 3. And for force 3, we've established that to be the 30 newtons. Now, the 30 newtons, as you can see, again, it's similar to the previous one. It's just an horizontal force, but this time it's going to the left. And what that means is it's just going to be negative 30 right there for the horizontal component. And for vertical, it's just going to be 0 newtons again. So that one's, again, nice and straightforward. And on to the final force, which is our 90 newtons. Now, for the 90 newtons at the top right there, again, this one's going down and it's going to the right. Our angle is 50 degrees. So it's just going to be a positive for the horizontal force component because it's going to the right. And then we're going to have 90 cos, and then the angle, which is 50 degrees. So for our calculation, 90 cos 50 turns out to be 57.85 newtons. So we go across now to the vertical force component, and because it's going down, it's a force that's going down, this one's going to be negative. So it's negative 90, and instead of cos, we have sin 50. And again, this one turns out to be a negative value, so negative 68.94. So now that we have our force components, what's next? We have to now sum these columns for the vertical components and the horizontal components. And what that looks like, the values that we're going to add for the horizontal components will be this 21.13 newtons added with that 40 newtons, added with that negative 30, and then this 57.85. So all we're doing is just putting these values in our calculators and get the total. And for the horizontal components, this turns out to be 88.98 newtons. So that's 88.98. That one's done. We go across now to the vertical components, and all we're adding is this negative 45.32. We have 0 there, 0 there, and we're adding this final value, negative 68.94. And the total for that is negative 114.26 newtons. So that one's all done. So now that we have our totals, what do we do with this information? Well, this is what we need to use now to calculate the magnitude and the direction of the resultant force. Now, to do that, I'm going to be very efficient with my calculations and ensure that you also understand how the direction of the resultant force works. So I'm going to sketch now a coordinate grid, and as before, this is our vertical component. This is our horizontal components. And because the value that we got for the horizontal component is a positive value, that value will go here on that side of the axis, which is to the right. It's positive there. So that's our 88.98. And because our vertical components, the total is negative, that value will come down here, which is our negative 114.26 newtons. So what that means then, the resultant is going to be going to the right and it's going down. So I'm going to sketch that now. So it looks something like so, to the right, and it's going down. And the angle that we're interested in is right there between the horizontal line and the resultant itself. So how do we calculate the actual value of the resultant represented by R? Now, an easy way to see this is to imagine we have a right-angled triangle right here, and our 90 degrees can be found right there. So our length now, the distance from right here, the origin, to the point 88.98 is actually the value of the length that we're going to use. So that's 88.98 goes there. And for the vertical axis, it's the same as our total, which was 114.26. And because we have a right angle triangle, you probably can see that that side with the green arrow is actually our hypotenuse. So then if it's the longest side, you know how to solve that. We'll have R equal the square root of 88.98 square, and plus that with our 114.26 square. We don't have to use the negative. Even if we do, it's gonna be squared, so it will be positive. So it doesn't really matter anyways. And our final answer for that will be 114.8 newtons. So this 114.8 newtons, this is actually representing the magnitude of the resultant force. So on to the direction now. How do we find the direction of this force, which is our angle right there with the green arrow? Now, we already established that this is a 90 degrees triangle. It's a right angle triangle. And what we have across from the angle is our opposite side right there, big O. And then the side above is our adjacent. So we're now working with opposite and adjacent. And if you remember our SOHCAHTOA stuff, you will identify immediately that we're going to use our tan because we're working with opposite and adjacent. And because we're finding the angle, it's just simply going to be tan inverse of opposite, which is 114.26, divided by adjacent, which is 88.98. And that gives us the angle. Quite straightforward. So that angle is 52.1 degrees. So now that we have calculated the magnitude and the direction of our resultant force, we now have to figure out exactly where to place this magnitude and direction of our resultant force on the diagram. And what I'm going to do is to go back to the diagram for a little further analysis so that you can see how this works. So this is our diagram that we started off with. And as you can see, our pivot point, which I'm going to highlight down here in green, is right there. That's our pivot point. And what we're going to do now is to calculate moment, and I'll explain that further in a second. But moment is just simply our force multiplied by perpendicular distance. So if we have a force and its distance from that pivot point, its perpendicular distance from that pivot point is known, then what we do is to just multiply the two, the force multiplied by the perpendicular distance, and what that looks like. So for the first force, this 50 newtons, it's acting right there at the pivot point, right on that highlighted green spot. So what that means, it does not have a distance from that exact same point. So its moment would be 0. But if we look above that now, that 40 newtons right here, highlighted in blue, it's going to the right. And I'm going to do a dotted sketch now for the perpendicular distance right there. So if we were to calculate that moment for the 40 newtons, which we'll do in a second, it's just going to be that 40 times, you see the distance right here in between, which is 2 meters. So if we look at the next two forces now, which is our 30 newtons, this 30 newtons, it's going directly across from that pivot point. So in terms of its perpendicular distance, again, there is none. And that's simply because it's acting right into that joint there. It's actually 180 degrees across from that pivot point. So therefore, our moment there would be 0. Now, for the next force, which is our 90 newtons, I'll just use this red to highlight it more. Right there. It is, in fact, that looks messy. So I'll just use a different color. I'll use yellow to highlight it. There we go. So that 90 newtons, remember previously we calculated two components for that 90 newtons. And those components, we already know the values, which we'll use shortly. I'm just going to show you now how to understand the perpendicular distance of them. So for the vertical components, I'm going to, let me clear all the markings so we can see this. So now for the vertical components, you will see this here, this path I'm highlighting in green, and the line of action going across to that same pivot point has to be at 90 degrees, which is right there. So it means that if we know the vertical force component, which we do, we would have to multiply that force component by 4, because that's the length of the horizontal distance, which happens to be perpendicular to the force. And equally, I'm going to use blue now, this next line is representing the horizontal force components, and 90 degrees to that same pivot point would be right here. So again, it's the horizontal force component, but times 2. So I'm going to do the calculations for that now and show you how that would look for the moments. So I'll carry on from this point here. So sum of the moments we're working out here. Forgive the handwriting. So again, for F1, which was our first force we talked about, we remember that that was 0. But when we move to F2, that 40 newtons, we know that it is 40 times 2. And in this instance, I'm just going to take whatever force turning clockwise, which all of them will, to be negative. So that would be negative 40, and that's 80, negative 80 Newton meters. So that's the first one there. Then for the next force, I'm just going to skip to F4 because the other one was 0 as well. We had the components, which were the horizontal, which was 57.85. So that's going to be 57.85 multiplied by the perpendicular distance of 2, which we talked about previously. And that turns out to be negative 115.7 Newton meters. And I will explain why I'm using negatives here in a second. And it's just basically how the forces are trying to rotate the system. So because I'm saying clockwise turn is negative, then because all the forces are trying to rotate the system in a clockwise motion, that's why these are negative. But I'll show you that much detail in a second. Then the next force, which was the vertical component, that was 68.94, and this is still for the fourth force, and the distance was 4. So that now turns out to be negative 275.76 Newton meters. So what we need here is just the total for these these moments, and that turns out to be negative 47 or negative 471.46 Newton meters. So this is representing the total moment. Okay. Now I've mentioned before that the forces were rotating the system clockwise, hence I'm using negative for clockwise rotation. We don't have to, could just say clockwise rotation is positive, doesn't really matter much. So what that means, I'll just come back here, is our pivot point, from our pivot point right there in green, you can just imagine from this point here, this force right there, it's going to be trying to rotate this thing like so in a clockwise manner. And as well as this force right here and both of its components still going to be trying to rotate this thing in a clockwise manner. And that's why I'm using negative, because I'm taking my clockwise turns to be negative, but you could use positives as well. So let's move on with the calculations then. Right, so now that we have the total moments, all we need to evaluate now is where we will place that line of action, and it's the perpendicular distance that we need. So because moments can be calculated using force times perpendicular distance, then therefore all we have to do is to just simply reorganize this formula to get the distance equals our moment divided by our force. And we have both of those values. The force that we're talking about is the resultant, and the moment is what we just calculated. So we just need to do 471.46, and that should be divided by the total for the resultant, which was 144.8. So we have a perpendicular distance of 3.26 meters. So that's the perpendicular distance. And what that looks like now, finally, I'll sketch that on the system so you can interpret it for yourself. It's just going to be a very rough sketch so you can understand exactly what we're on about. So we do know our resultant force was going down and to the right, so we can just sketch that something like so in green. And we also know the perpendicular distance here, so it should look something like that, where the 90 degrees is there. And if I'm to do the equal and opposite force, then it should just be in the opposite direction like that, which is our equilibriant. And that's just a rough sketch for you to understand what we just did. So if you got any value from this video, if you have learned anything, please like the video, share to someone who you think might benefit from this video. And until next time, I'll see you in the next video.